Hi, I'm Professor Mehmet Engin. Today's seminar title is Rotational Breast Infrared Thermal Imaging, RBT. Now, this all talk of seminar, the motivation, the next one, thermal profile of human breast, principle of breast thermography, basis of conventional breast thermography, rotational breast thermography, RBT, breast abnormality analysis in rotational thermograms, future analysis for classification, classification for breast conditions, future reduction using principal component analysis (PCA), breast pathology localization using rotational thermogram series, results and localization, and finally conclusions. The motivation. Breast cancer is considered to be one of the major causes for high mortality rates in young women in the developing countries. Survival rate in the breast cancer patients may be improved significantly by early detection. In order to detect cancer in its initial stage, breast screening is recommended for women over 40 years of age. Due to limitation of existing breast cancer screening techniques, adjunct or complementary modalities such as thermography are being explored. In evaluation of local surface temperature due to underlying pathology is considered one of the earliest indication of an underlying cancer. Such regions are represented as hotspots and the conventional thermogram. Detection of these hotspots from conventional breast thermogram is quite challenging, mainly due to incomplete image acquisition. A novel technique called rotational thermography has been developed to address this problem. Now, thermal profile of human breast. The core temperature of human body is reported to be around 37 degrees of Celsius when the ambient temperature is maintained at 25 degrees of Celsius. The transfer of heat from core of the body to skin surface is a complex thermobiological process. When subjected to extreme environmental temperatures, the vasoregulatory system of our body help to maintain the thermal equilibrium by triggering shivering or sweating as reflex mechanisms. The optimum temperature range in which a slightly dressed human body can maintain thermal equilibrium is 20 between and 25 degrees of Celsius. Hence, thermographic studies are conducted in the controlled environments maintained within this temperature range. The mean temperature of human breast is found to vary from person to person based on several factors such as environmental conditions, physical exertion, menstrual cycle, anxiety, etc. Also, different regions with the breast exhibit different temperatures. The average temperatures of breast surface is reported to be around 30 degrees of Celsius in controlled environment at 20 degrees Celsius. Several researchers have established that the surface temperatures of cancerous region is significantly higher than that of the surrounding normal regions. Hence, an abnormal breast condition may be detected by analyzing the temperature differences within the breast region. The further, a temperature difference of more than 0.5 degrees of Celsius between right and the left breast is reported to be indicative of abnormality. Hence, exploring the thermal asymmetry between the contralateral breast is widely practiced for breast cancer detection. Due to the advancement in sensor technology, infrared cameras with enhanced thermal resolution of less than 0.5 degrees of Celsius are available. These are capable of sensing the subtle temperature variations and are used for evaluating breast conditions in breast thermography. Now, principles of breast thermography. The first instance of using infrared imaging for cancer diagnostics can be traced to 1956, when it was discovered that surface temperature over cancerous tissue in a breast was higher than the surrounding normal regions. The high rate of the metabolic activity around cancerous tumors triggers a huge demand for supply of nutrients. Consequently, an increased blood flow is ensured in order to nourish these cancer cells by recruiting dormant vessels and creating new ones, neoangiogenesis. This process leads to vascular asymmetry and increase in regional surface temperatures in the breasts, which may be considered as an earlier sign of breast cancer. Breast thermography involves capturing these variations and interpreting them the early detection of breast cancer or for monitoring its progress. State-of-the-art breast thermography uses highly sensitive infrared cameras and software systems to represent thermal variations in the breast surface in the form of the high-resolution images called breast thermograms. The procedure is non-invasive, comfortable, and radiation safe. An abnormal breast thermogram has been reported to be an important high-risk marker for cancer that might develop in the future. Both passive and active methods are being practiced in breast thermography. In passive thermography, regions of interest are naturally at higher or lower temperature than the background. Since the infrared rays emitted from these regions are picked up effectively by camera systems. An active approach is necessary when such regions are usually in equilibrium with the surroundings. Thus, in active thermography, an energy source is used to produce a thermal contrast between the region of interest and the background by applying a cold challenge. It is usually implemented as blow of hot air or chemical vaporization and the skin surface. While thermography is a promising screening tool for the breast cancer, diagnosis is usually done manually by skilled professionals. Hence, interpretation made from the thermogram highly subjective in nature. In order to overcome factors such as shortage of trained personnel and operator variability, computer-aided diagnostics CAD systems needs to be developed. An advancement made in thermal imaging systems and pattern analysis techniques may be used to build a reliable system for breast cancer detection based on thermography. Such systems can be used for breast cancer screening in developing countries, especially by primary healthcare professionals in rural areas where specialized healthcare is lacking. Several researchers have worked on the developing CAD systems for breast cancer detection using thermogram acquired by conventional breast thermography techniques. Now, basis of conventional breast thermography. In the conventional techniques for breast thermography, the patient is sitting in front of the infrared camera at distance of between 80 and 100 centimeter. This distance is chosen so as to image the complete torso of subjects with good resolution at the field of view of camera. The schematic representation of conventional breast thermography techniques is shown in the figure 1. In this method, infrared images of the breast are acquired by three views, such as contralateral, mediolateral oblique, and axillary. Most of the CAD systems presented in literature use contralateral or frontal thermograms and are confronted with two problems. First, tumors in the inferior region of the breast are obscured behind the natural sag and often go undetected. Secondly, the neck carotid and inframammary folds are visible in the images. These are normally hot regions that may be later on diagnosed if not removed. Segmentation of the breast from these areas is a prerequisite for effective CAT systems and is quite a challenge till date. The image acquisition and interpretation processes are operator dependent and are found to be vary across patients. In order to address these issues, a new thermal imaging technique called rotational thermography has been evolved. Rotational thermography. A novel step known as mammary rotational infrared thermogram (MAMRIT) unit is used for acquiring rotational breast thermograms. The unit comprises an imaging chamber with the patient table and it is top and is shown on the figure 2. Now, this is chamber. Some of views of this chamber unit is shown in the figure 2. Here. The ambient temperature and humidity inside the chamber are controlled with an built air conditioner. The subject lies in prone position and the patient table of the memory unit, with one breast suspended through the small circular aperture into the imaging chamber beneath. An infrared camera is fixed at the free end of the robotic arm situated inside the memory chamber. The arm is programmed to revolve around the suspended breast at angular steps of 30 degrees. The infrared camera captures images of breasts at every step, thus 12 views of the breast are obtained in one rotation, ensuring complete imaging of the breast. The acquisition of temperature information is repeated after lowering the ambient temperature to understand the tissue response to external stimuli. All the images are stored along the patient information, the camera position, ambient temperature, and time of execution. The set of thermograms obtained before and after lowering of ambient temperatures are called pre-cool and post-cool series, respectively. The same procedure is repeated for the other breast. Specific patterns of temperature variation is observed along the vertical direction in rotational breast thermograms of normal subjects. The nipple region is found to be coldest and the temperature increases in the region closer to the chest wall. This pattern is found to be extend across the breast when all 12 waves are observed. In the case of abnormality, bands that represent higher temperatures are found protruding into the zones of lower temperatures, thereby disturbing the characteristic temperature pattern. Figure 3 shows some image series of these systems. In these images, the complete sequence of pre-cool rotational images of single breast or left breast at 4 different angles, respectively. The rotational breast thermography techniques contains more diagnostic information than the conventional technique due to following reasons. First, changes of missing of tumor are much less as the breast is imaged completely. Second one, as images are captured by moving camera around the suspended breast, all tumors that are located within 4.5 centimeters from breast surface are detected at less than the 5 closest waves. Whereas in the conventional method, the heat emissions from such depths are scattered and lost of the underlying tissues. Third one, cold challenges may be easily implemented as the breast is imaged in the temperature control chamber. Last one, movement artifacts are generally reduced as the patient is made to lie comfortably in prone postures during image acquisition. Now, breast abnormality analysis in rotational thermograms. During the last 2 decades, several computer-aided systems have been developed for screening of abnormality from conventional breast thermograms. Such systems include general image processing techniques such as segmentation, feature extraction, and classification. Several segmentation methods have been proposed to extract whole breast and the specific region of interest as well. Spatial domain statistical features, wavelet-based features, higher-order spectral features, bispectral invariant features, and fractal dimensions have been employed for classifying breast thermograms. Numerical modeling of thermal properties of the breast has been used to aid interpretation from breast thermograms. The relationship between texture features and surface temperatures changes has been well established in literature. Hence, texture features are extracted from regions of evaluated temperatures in rotational thermograms for breast screening. Various breast abnormalities exhibit distinct temperature profiles and may be broadly characterized as benign or malignant. The local temperature rise is less than 1 degrees of Celsius is benign regions, while it's more than 1.5 degrees of Celsius in the case of malignancy. This margin between benign and malignant conditions may be even less than malignancy is in the initial stages. Further, the patterns of thermal variations between normal and benign conditions are often indistinguishable. Hence, the characterization study is also important for detection of breast cancer. Examples of normal, benign, and malignant thermograms are shown in the figure 4. From the observation made from literature survey and conventional thermography-based systems and preliminary study on rotational thermography, a CAT system has been developed for screening and characterization of abnormality in rotational breast thermograms. The general block diagram of this system is shown figure 5. Now, feature analysis for classification. Features extracted from normal and abnormal region of interest of the breast in the various domains are analyzed and classified using support vector machines, for example, classifiers. This is classified types. Average value of each feature is computed for both classes in all the regions. Features extracted in special domain and the transfer domains are analyzed statistically using students' t-test at 95% confidence level. The null hypothesis is framed such that the features extracted from the normal and abnormal groups belong to same classes If the p-value returned by the test is found to be less than 0.05, this null hypothesis is rejected. These features with p smaller than 0.05 are found to be statistically significant than the others and can discriminate an abnormal region of interest from the normal one more effectively. Feature analysis by student t-test proved that the first-order statistical features were statistically significant in almost all domains. As the first-order statistical features were found to be statistical and significant, these were eliminated from further investigations. A two-stage classification scheme has been implemented using texture and bispectral features. In the first stage, the screening ability of the system has been tested in all domains, followed by the evaluation of characterization ability. Now, this is classification for breast conditions. The support vector Michis classifier is used to automatic detection of abnormal conditions in thermograms. This classifier is supervised learning algorithm that finds wide application in pattern recognition problems. It generates a robust mapping function from set of training data. This classifier is a one grid used in classification problems where the input data is not linearly separable. In such cases, nonlinear kernel functions may be used to transform the input data to higher dimensional feature space where the separability is better. The order of these functions may be varied iteratively until the distance between the decision surface and nearest sample is maximized. Thus, support vector machines construct n-dimensional hyperplane for optimal separation of input data into classes. The performance of this classifier has been evaluated by the finding accuracy, sensitivity, and specificity measures from confusion matrices. The observation made in 4 categories, such as true positives, true negatives, false positives, and false negatives, and represented 2 times 2 matrices. Accuracy is the measure of true results obtained by the test in the entire population. Sensitivity represents the probability that the test will produce positive results when used in a diseased population. Specificity gives the probability that a test will produce the negative results when conducted in normal population. Now, feature reduction by principal component analysis, PCA. Principal component analysis is a statistical procedure used to convert a set of highly correlated input variables into a smaller set of uncorrelated variables, popularly called principal components. These orthogonal transformation results in a reduced set of variables as the number of principal components obtained is usually less than the number of original inputs. These components are formed by linear combinations of all input features and are arranged in decreasing order of their variance. The composition of these principal components may be analyzed by observing the respective eigenvectors. PCA is generally used as a feature reduction technique in classification problem when the input feature set of large and redundant. Now, selection of optimal features using genetic algorithm. Although PCA gives a reduced feature set, all features have been extracted in the first place in order to form the principal components. PCA provides fewer discriminative inputs that reduce classifier complexity but fail to be of any aid in the exhaustive feature extraction process. Hence, an effective search algorithm may be employed to select the most discriminative subset of features. Genetic algorithms, GA, is used to identify the optimal features that can lead to best classification accuracy. GA is a search algorithm that models the natural process of biological evolution using operators such as selection, mutation, and crossover to find the optimal solution for a specific problem. In GA, each feature set is represented as a chromosome. A chromosome is represented in the form of binary strings of length equal to the number of features. A fitness function, usually a maximizing or minimizing function, is defined for the problem. The fitness value of each chromosome is computed. The selection of the chromosome is based on the ranking of its fitness value. The GE-based approach begins with creation of an initial random population, and it is evaluation using the fitness function based on the classifier error. Using selection methods such as roulette, wheel, tournament, etc., chromosomes pairs are selected to undergo crossover and mutation to form new population. The process is repeated iteratively until the GE convergence and the best chromosome is returned. The composition of the best chromosome may be examined to identify the optimal features. Support vector matching is trained and tested with a set of feature vectors extracted from normal and abnormal thermograms by the leave one out method, first for screening and then the characterizing an abnormality as benign or malignant. Now, localization of breast pathology using rotational thermogram series. As discussed earlier, images are acquired at special increments of 30 degrees, resulting in series of 12 thermograms. Given size of the breast, there is a partial overlap of the regions and successive thermograms of series. To ensure that the entire breast is examined 30% of the total area is extracted as region of interest from the center of the breast in each view. However, it is found that the region of interest cannot be identified uniquely with the respective breast weaves due to overlaps with the region of interest of succeeding and preceding weaves. Nevertheless, there is a non-overlapped central region in each region of interest. If an abnormality is represented as a hotspot in the confined small area, it will be detected in the central portion of one of the weaves. Thus, the accuracy of the locating is better. Secondly, if an abnormality is observed at the periphery of breast at one weave, it will be seen in the central portion of breast in one or two successive images down the series. Thirdly, if an abnormality is represented as a larger hot area, it will be seen in the central portion of more than one weave. In such cases, accuracy of locating it will be erroneous. Finally, as curved base feature texture features found to be performed best for classification purposes, these were extracted from the region of interest. These features, namely curve wavelet based features vectors, are given as test inputs to support vector matching classifier in order to detect abnormal weaves. The classifier is trained with curved texture features extracted from 36 thermogram in each normal and malignant group. The special weaves where the abnormality was detected by the system are noted to further analysis. Finally, optimal feature selected genetic algorithms have also been used to improve the localization ability. Now, results of the localization studies. The study includes prequel series of thermograms of 36 malignant patients, 12 thermograms per patient. A report indicating hyperthermal Vs, as interpreted by the thermograms, is made available for each subject. According to this report, several Vs are indicated to be hyperthermal. Details of the thermogram used in the work are given in Table 2. Table 2 establishes that the distribution of the heat and the breast surface is based on the severity of the underlying tumor. Results of the localization study are analyzed by evaluating the performance of the system from classification confusion matrices. It was observed that all abnormal waves were detected by the systems when curvelet-based texture features were employed. Out of 224 normal thermograms, 288 were identified correctly by the system, resulting in accuracy of 91%, sensitivity 100%, and specificity 88.9%. Improved performance was obtained when optimal features were used for classification, as shown in Table 3. It is found that all the identified abnormal Vs were detected, while 30 normal Vs were misclassified as abnormal. Hence, detailed case studies were conducted to validate the performance of the systems with the opinion of expert radiologists. The abnormal Vs detected by the systems were compared with expert opinion and respective ultrasound findings. All regions which were detected as abnormal by the proposed systems, expert interpretation, and ultrasound as well were found to be malignant, resulting in 100% sensitivity. This was verified with biopsy results in each case. It is found that a normal breast region with increased vasculature is reported to be hyperthermal on the thermograms, but normal on ultrasound. Finally, this is conclusions of the seminar. As rotational breast thermography acquires images of the breast in the multiple views, its ability for localization of abnormality has also been explored. Screening performance of rotational thermography is found to be superior with curve-based texture features. The ability of rotational thermography for detecting malignancy from normal and benign conditions has also been found to be effective. Localization of the abnormality is a promising area for further research in rotational thermography. Thank you. See you again. Bye.